Welcome to Hyliion's Tech Fireside Chat. Today I'm joined by Josh Mook, our Chief Technology Officer, and we're going to be diving into our KARNO generator. So this is a solution that we see being able to solve distributed power generation, where you actually make your own electricity on site and reduce your dependency on the grid. So this is our KARNO. It is a linear heat generator. A lot of people think about it as it's like an internal combustion engine. That's not the case at all. You actually need to take all you know about internal combustion engines, throw that to the side. This is a heat gen set we'll talk about in more detail. But there are really 5 key things we're going to be covering today that differentiate this. So the first is it has superior efficiency. So we're getting near power plant level efficiency out of this small generator that would normally take hundreds of acres out of a power plant. This solution is truly fuel agnostic, can run on fuels like natural gas, hydrogen, even ammonia. And when it's running on fuels like hydrogen and ammonia, you are able to unlock having 0 carbon emissions, which leads us into the third one, the low emissions profile. 0 carbon emissions on some fuels, and our unique flameless oxidation process that we're going to show you today unlocks the ability to have much lower emissions than a normal internal combustion engine. The fourth is durability. So this genset has no oils, no lubricants, and it's really designed to deploy it and then forget about it. And then the fifth is it's stackable. So think about it where each one of these shafts is about 50 kilowatts of power output. As you need more power, you just put more shafts together to make the desired power output level. So those are the 5 benefits we're going to kind of keep bringing up in today's session. But with that, I'll turn it over to Josh to talk about what is a heat engine, how does it work?
Yeah, thanks, Thomas. So as we mentioned, this is not an internal combustion engine. So what we're going to do is walk through the sort of the thermodynamics, what makes the system work side to side, and then get into how we make that heat secondarily. So the system is made up of 4 major components: your electric machine, your compression space, your expansion space, and your reactor. So we'll go through those one by one. First, let's start with the electric machine. So inside of the electric machine, we have a shaft, and I have an example shaft here, that is oscillating back and forth inside the system. These have magnets attached to them, and those magnets move within a set of coils, which create the electricity to either go to your site or back to the grid, depending on the application. But in order to make that movement, what we do is we expand and contract a sealed gas inside of the system. And we do that through the compression and expansion space here. So in the compression space, we're taking that trapped gas, we're cooling it down through a closed water loop, or in a combined heat and power scenario, something that's connected to your building's heating. In that case, the gas contracts and cools down and helps pull the shaft to one direction. And then simultaneously, we're heating and expanding the gas on the other side to increase the gas pressure and again apply force, which moves that shaft to the other side. Both of the sides here are operating together but out of phase with each other, such that that shaft can oscillate back and forth at its natural frequency with high efficiency. But we do have to make heat in most cases in order to be able to initiate this movement. And so we do that through our reactor here on the end. This is where we'll bring fuel and air together, and we'll react those using the flameless oxidation process. And that heat is then captured by our hot side and transferred into the system. Traditionally, heat generators have been really difficult to implement because it's quite hard to move hot gas through the system and just transfer heat across metal boundaries. In this case, we're using additive manufacturing as a key unlock for us, both from a design and manufacturing perspective, and we'll dig into those both components and the manufacturing process coming up.
So before we go look at some parts, as you think about that shaft being slowed down on one end, how much force is being applied to it to change the motion?
Yeah, so as the shaft comes to a stop and then we re-accelerate it, we're putting about 4,000 pounds of linear force in there to move it to the other side.
Very neat. All right, let's go look at some parts. We now want to show you what some of these parts look like within the KARNO. So as Josh mentioned, you really have 4 main components. Your linear motor, which is just coils and magnets, and then you have these 3 parts on the outside, which these are the parts made through additive manufacturing. Now, one of the questions we get asked a lot is, well, do you need to use additive? Can't you just do conventional manufacturing? And the unique thing with each one of these parts is there are geometries within these that really just offer major unlocks to get us that efficiency, to help improve the size of the system that you couldn't get if you made this through conventional manufacturing. So, Josh, maybe to start us off, can you share a little history of where additive was 10 years ago, where we are today? And I mean, this is something that you personally have had a huge influence on.
Yeah, absolutely. So 10 years ago, additive was really being brought up through the aerospace industry, specifically for use in jet engines. So critical components that had high expectations in terms of durability and performance and all the same things we're talking about here, but really high consequence of failure. And so as a result, we really focused on developing the materials, developing the process, developing the machines to be able to produce these highly capable parts like you see here in front of you today.
So the other question we get asked a lot is cost, right? So if we take a component like this one, from the outside, it looks really basic, right? But here's a cutaway of the inside. And you can see, I mean, that is extremely complex, right? You could only unlock that through additive manufacturing. You couldn't even make that through conventional practices. But cost-wise, where are we at on this curve of is it economical to use additive?
Right, yeah, so there's a couple things that drive cost in additive. One is the speed of the process. So additive is very much on sort of a Moore's law of its own, where it's increasing in speed dramatically year over year. And we're certainly taking advantage of that in our process. The other is how much material do you use, and are you using material for non-really good additive application? So this part's a great example where you see just an unbelievable amount of complexity inside of it here with the heat exchanger and the other bits to enable the flameless oxidation process. But what you don't see is a lot of sort of unused or I'll say wasted material that's going to drive cost. And so by keeping the material usage down, by keeping the machine speed up, we can keep cost at a good point.
So 10 years ago, additive was really only used for aerospace, healthcare. Today, you even have automobile manufacturing companies starting to use additive for their production lines, or production processes. The thing is, though, you don't want to make conventional parts through additive, right? If you can make it through standard manufacturing, that's not the right part to print. It's parts like this that have really unique geometries that you want to make with additive. So we have some of our additive machines here behind us. Why don't we go take a look at how these parts are actually made. Behind us here are some of our additive machines. You can see they come in different sizes, different scales, as well as different speeds. But let's first start off with talking about additive, right? So it's kind of like 3D printing. I'm sure many of you are familiar with plastic 3D printing machines where you melt plastic, it goes around, lays down a layer, and then you do the next layer. Well, metal additive manufacturing is not that dissimilar. But the way it works is you lay down a bed of powder, a bed of metal that's in like a dust format, and then a laser goes around and it actually zaps the metal, welds it to the layer below. Then once it's done with a layer, the part drops down a little and you lay down a new bed of powder to start that process over again. So as you're making a part, like how many layers are actually in one of these
Yeah, it
parts?
depends on the size of the part, but we will normally have 5,000 or so layers at a thickness of 20 to 100 microns per layer.
So then the unlock here is, we talked about speed earlier. So how do you get these machines to be faster, or what has happened to make them faster?
Yeah, it's all wrapped up around really two things. One is the design and the other is the machine. And so from the machine perspective, it's how much energy can you put into that weld at any given time. And so we can get energy by both higher laser power as well as more lasers working together simultaneously on a part. And the machines over the years, you've seen that progression of more lasers, higher power, and then we take advantage of that through our material properties. And then from the design perspective, it's really only using, again, the material that you need, so you're not wasting time melting components that you don't need, but also using the energy effectively. We nest parts, or we sometimes have multiple parts print simultaneously, and that helps reduce the cost.
Now, within these machines, there's kind of two aspects. You have in here where the actual printing process is happening, but then you also have the extraction area. So once a part's made, you actually have to remove it from that powder, and this creates another unlock, which is very limited waste.
Yeah, so it's not atypical that we have 99% reuse on our powder, and we'll continue to reuse it over and over again until it's essentially eliminated. Again, only use the material you need and not anything more.
Yeah. So that gives you a little overview of how these parts are actually made. we next want to go take a look at the reaction process, that flameless oxidation process we mentioned, and how that works within the KARNO. We're now here in one of our test areas in the facility where we're actually able to showcase the flameless oxidation process happening. So the components behind us here are kind of the outermost units of the KARNO generator, which is where the fuel is reacting. You can see that process happening. So we're bringing in natural gas, we're combining that with air, and then what's unique is we're reacting the fuel. You can see all the metal components around are actually glowing orange because they're so hot. But because of that unique flameless oxidation process, you actually really can't even see a flame. And that's one of the unique things that offer us that low emissions within the KARNO generator.
Yeah, another interesting observation in this process versus like an internal combustion engine is you'll notice this process is continuous and complete, but it's not a series of explosions like you would normally see in an internal combustion.
So behind us here, this is operating on natural gas. We're now going to shift and take a look at what this process actually looks like if we run it on a conventional fuel like diesel.
As you can see here, we have the diesel system running in the flameless oxidation process. It's very similar to that you saw in natural gas. You're seeing a very clean flame with minimal soot and particulate, which just shows the cleanliness of this system versus a traditional internal combustion process.
The last thing we wanted to showcase today is the KARNO generator actually running. And then we actually brought in a diesel engine as well to be able to do an A to B comparison to showcase the size difference as well as the noise difference between the two. So before we fire up the KARNO generator behind me here, so this is a 4-shaft alpha unit. So it's one of our pre-production units. This generator will produce about 125 kilowatts of power output. The production ones that are going to be about the same size footprint as this will be about 200 kilowatts of power output, but this gives you a good sense of just the size scale and the noise levels coming out of it. The diesel engine here is a 180 kilowatt engine, and one of the other things you'll notice is we've got the doors open on this one, as well as we don't have any shielding on the KARNO. So as you're looking at the decibel reader, we anticipate the KARNO deployed in a stationary production box with sound deadening around it will be about 67 decibels at about 6 feet away. You can see our room is already even louder than that level, so you're going to hear it be a little bit louder than that, but you'll get a good comparison of a diesel versus the KARNO with no sound deadening around it. One of the other things that we talked about in today's presentation was durability. And so Josh, can you cover a little bit about why we expect our system to be more durable than a conventional diesel?
Absolutely. So when you think about the KARNO system, you know, we talked about how it's a sealed system with no oils or other fluids inside that need to be changed regularly. And so as a result, you're going to get about 20,000 hours of average life out of that system before requiring an overhaul. If you compare that to an internal combustion system where you're going to have a few thousand hours of life, so significant reduction compared to the KARNO prior to overhaul, but in addition to that, you're going to have every 100 or so hours regular oil changes or other maintenance that needs to occur. All of that you can just avoid on the KARNO completely.
Terrific. All right, well with that, we'll go ahead and fire up the KARNO. We appreciate you joining us here today for this tech overview of the KARNO generator, and we'll now go ahead and take some questions. Well, thank you again all for joining us today. Hopefully that was a good overview of just how the KARNO technology works, getting a little bit more of an in-depth view of what differentiates this technology. But we wanted to focus today's call on actually taking questions from all of you and starting to address them and hopefully shedding some more light on the solution. So with that, we've got a bunch of questions that have already come in. As a reminder, if you've joined into the webcast, please go in and submit any questions you have, and we'll do our best to answer them. But we'll start off the questions. We got our first one that came in from Twitter from Magni, who is asking, how fast can you print the KARNO? How many prints do you need to scale up? And at last, do you need any certifications to deliver, and how close are you to achieve this? So maybe we'll start off with, let's do printing speed, and then we'll talk about certifications.
Yeah, sure thing. So for printing speed, today I would say our longest parts take a few hours. I'm sorry, a few days to print from start to finish, and those are increasing, like we mentioned in the video, year over year. We anticipate being in the hours mark in the not too distant future.
So print time is continuing to get faster. As
Yep.
you said during the presentation, it's like the Moore's law, right? It's
Right.
Printers are getting much faster. Even the ones you saw in the video, they have different speeds just because of some were bought more recently versus
Yep.
some were a little older. Another question also coming in from Twitter from David is, what are the specific applications where the KARNO generator is most likely to be adopted first? So this is a great question, and we see a few different opportunities. One is prime power. So that would be like, think about a hotel, a hospital, a warehouse, a facility like the one we're in, where you actually use the KARNO generator as your primary power source, and now the grid actually becomes your backup power supply. So prime power is one that's obviously a massive market opportunity. But then there are some other unique sectors, like, for instance, this morning we announced that we successfully ran the KARNO generator using gas that would normally be flared. So it was field gas from the oil and gas industry. And it specifically came from the Permian Basin from one of our partners that we're working with, who we expect will be one of the initial customers, and we'll share more on that in the not too distant future. But using flare gas or field gas to produce electricity, you can similarly do that at like waste gas out of a landfill. Then EV charging we see as a great opportunity, as well as matching renewables, right? So if you think about wind and solar, it's a great source of electricity, except for if the wind's not blowing or the sun's not shining, so we can offset that. So those are a few of the initial market sectors we plan on going after. But I think EV charging, waste gas, and then prime power are some of the really exciting ones. All right. Next question that we got coming in from David is, compared to traditional generators, what is the expected efficiency increase of the KARNO generator? So Josh, you want to take that?
So all of this obviously depends on your baseline, but the way we think about the KARNO generator and the system is we look at it always as an entire system. And so when we talk about numbers approaching 50%, that's sort of the net system, right? If you think about generators that you would maybe use today, traditional diesel generators, it's not atypical that you'll see half of that, or at a minimum a 20-25% reduction relative to where we're going to be in our system. So pretty tremendous step change that really moves the needle on things like operating costs and just fuel usage as well as emissions.
And in the video, we had the diesel gen.
Yep.
I think you actually looked up the spec sheet. What was the efficiency?
That one's around 20 to 25% all when it's net, all said and done.
So we're more close, 50-ish number is our ballpark. So, all right. So next question here is coming from Donovan Schaefer from Northland Capital. And Donovan's question was, you've talked before about putting power back onto the grid within your facility in Ohio. Can you clarify if that was done in conjunction with the utility and all a way that it was in line with the utility's requirements, and what specifications they would require for tying into the grid? So you work specifically on that.
Absolutely. So the answer is yes, that, we had to work with, local authorities as well as the utility to get what's called a grid interconnect, which allows you to connect to the grid and be able to push or pull power from the grid. And so that was done all by, there's a IEEE standards that we comply to, as well as, safety requirements, not only for the device, but for the line workers. And yeah, all of that was complied and worked through it to do that demonstration.
Sure. So next question coming in from Ralph is, can a KARNO be used for peak shaving operations? And absolutely, yeah. So I talked a little bit about, these different use cases. Peak shaving is another one that we can go after. And, for anyone who maybe isn't familiar with peak shaving, so throughout the day, your power consumption fluctuates, right, in a facility, at your house. And so in some instances, utilities will actually charge you more for when you're consuming more power. And so peak shaving allows you to kind of offset that and keep your power consumption more steady that you're pulling from the grid. So we can absolutely do that. One other thing that I think this brings up a good opportunity to highlight is the philosophy we have around the KARNO is if you own one of these generators, you want to run it, right? It's very different than, a diesel genset like the one we showed in the video, which is more, you're only going to really use that if you can't get your grid hookup, if the grid's down and you need backup power, like, the maintenance, the costs associated with those gensets just don't bode well for prime power. Versus with the KARNO, it's more the opposite of, if you own it, we think you should be running it. It should be a very low cost electricity and a very low maintenance cycle. All right. So next question is coming in from Graham from Raymond James. And question is, for the Permian Basin natural gas tests announced this morning, does the gas have to meet any specific standards regarding impurities such as sulfur content, nitrogen hydrates, or even heavier hydrocarbons?
Yeah, so
or hydrocarbons, not hydrocarbons.
Hydrocarbons, right? Yeah. So, I mean, one of the advantages of the KARNO system in the fact that it's a sealed system, so all of the working fluid is sealed from where the high gas is generated, is that you're fairly tolerant to impurities and other things in the gas. And so that combined with using some, advanced material solutions for our hot side, give us good durability to things like sulfur, as an example. That being said, the gas, any of the items in the gas that are, let's say, inert or not participating in the reaction process, they're going to pass right through the system and out the other side. So we do have to still be cognizant from an emissions perspective of what's in that initial gas. But for the most part, the generator is fairly insensitive to the content of that gas.
And a follow-up question that came in on that is, can you talk about the durability of the KARNO when used in oil and gas applications?
Yeah. So, I mean, this is why we're doing all the testing, right? So we can continue to learn, how the durability for different gases, how it comes out. But in general, again, because that system is sealed and isolated from where the gas is made, you're not going to see an impact on like the pistons or the other working elements of the generator. What we do watch very closely is any reaction that we have with the metal components of what we call the heater or the hot side heat exchanger, to watch for any degradation there. But so far, I think we're lined up really well for success for a broad set of gases.
And maybe just on that, can you talk to, like, other people refer to gensets as fuel agnostic?
Right.
How do they mean fuel agnostic versus how do we mean fuel agnostic?
Yeah, when we mean fuel agnostic, we mean part number identical, right? And so, in other words, the same piece of hardware that was installed on one fuel can be used on another fuel as well. More typically, what you see is when people refer to fuel agnostic, they say, well, maybe the block is agnostic and you need to go replace the head and the valve train and all these other components. That is not our case. We really can handle most of that in software by optimizing like the fueling schedules and everything to accommodate the different gases.
Yeah. And we've even seen some people say, well, we can run on hydrogen, but only up to a certain percentage of hydrogen. That's not the case for the KARNO. We can run 100% hydrogen.
Yep.
Another question that came in from Twitter from Maestro, which is, will the KARNO R&D for stationary applications also extend or continue for vehicles and marine applications? Could we conceive a reintroduction of the KARNO Hypertruck as a system kit? So this is a great question. I'll maybe start with just a little background over the past month for Hyliion. So as I'm sure many of you are aware, we had a pretty significant shift within the organization where, we had kind of two businesses going. We had both powertrain and then the KARNO generator. We decided, due to some changes we were seeing in the powertrain side of things, to really refocus our efforts purely towards KARNO for the time being. We do still have the Hypertruck technology, but we've put that on the shelf and saved it for later. So as we think about how KARNO is going to evolve, well, the reason that we initially acquired the KARNO technology out of GE was we saw this as a great fit for on-road applications. So the generator that we're actually developing is designed to not only meet stationary specs, but also to meet vehicle, or as mentioned in the question, marine type specs. And actually, fun fact, that diesel fuel you saw running was specifically focused towards marine diesel fuel. So we see marine as being a great use case, but then also with the vehicle side of things, we'll obviously look at the market, see how it evolves, and look for opportunities to bring the KARNO generator back into the vehicle space when the time is right. One thing that I think sheds a lot of light on this, though, is just the timeline for certification, which maybe you can touch on. Like, what's the certification needed for stationary versus vehicle?
Yeah, as you would imagine, for on the road applications, the certification requirements are much more stringent in terms of how that's going to interact in like a crash or other safety phenomenon, and so you don't have a lot of that on the stationary application. So we're able to very quickly comply with the stationary requirements while we work potentially others in parallel for on road applications.
Yeah. And not a question that has come in, but maybe talking about emissions on that end as well. So, their kind of CARB has laid out future emissions plans, and maybe just talk to where are we at on this spectrum versus those futuristic limits.
Yeah, absolutely. So we're designing to the most stringent, even future limits that we've seen. So at the moment, we have a good path to compliance for it, even all the proposed rules that we're aware of, and certainly have significant margin relative to all today's requirements.
Yep. And one question we get a lot is, do you need a catalyst? Do you need a DEF system? Because the latest discussion in the industry is like internal engines running on hydrogen. They're going to need DEF systems, right? Where do we sit on that?
Yeah, today we don't use any after treatment systems whatsoever today, and we're really trying to hold ourselves to that standard, because that just gives us a tremendous amount of additional runway if we want to go even lower in the future.
Great. All right, another question that came in from Twitter from Silent Alert is the intent to fully print the units or use traditional subtractive methods of manufacturing? Also, can you speak more about the Libertine partnership and how will that impact the future of the KARNO? So you want to talk about the printing one, then I'll talk about the Libertine side of things?
Sure, yeah. So for printing, I mean, we already use a mix of additive and traditional today. I think in the video I try to explain you really want to use additive where the complexity level buys its way on to the application, right? What you're doing really takes a big advantage from the complexity or the geometrical freedom that additive provides. So the one that's the most obvious is heat exchange. You can get levels of heat exchange using additive design techniques that well exceed anything you've ever seen from a traditional manufacturing standpoint. So we use additive there. There are other parts of the system, like, simple pressure vessels or structural components, where it wouldn't make sense, and we use traditional means there. So you already see a mix today, and we spend a lot of time trying to optimize that mix for, maximizing performance while minimizing cost.
Perfect. And then shifting over to the linear generator side of things. So the unit that was showcased in this video, similarly the unit we showcased at ACT Expo and publicly, that does have a Libertine linear motor in the center of it. As we move this technology into production, though, as we think about the units that we'll be deploying later next year and into 2025, our plan is actually to shift to using a in-house design and built linear generator system. And Josh's team are well underway with the design and development of that solution. And that will really give us the ability to not only own the technology around the linear generator, but then to have those three elements, right? The chiller, the heater, and the reactor. Those will be all Hyliion components as well.
Yep.
All right. Next question that came in from Matthew is, do you anticipate the KARNO to successfully meet the military standards, such as needed in deploying in environments like high temperatures and dust found in the desert?
Yeah, the simple answer is yes. And our design already has taken all those mil standards into account, and we're designing to those right out of the gate.
All right. Another question is from Steven is, for the KARNO, can you supply enough KARNOs for a project in West Texas, like out in the Permian Basin, where you'd maybe need like 10 megawatts of power output? So you want to talk about how we can scale up to that?
Yeah, absolutely. So as we've mentioned before, we today have these 200 kilowatt sort of building blocks, is the way I think about it. And we assemble those together into essentially whatever power level that the application would call for. There is no sort of upper limit on that from a like feasibility or a technology perspective. So then it's really going to come down to just does it make sense for that application, et cetera, et cetera. But we're very excited about the scalability of the system up to really whatever, sky's the limit.
Perfect. All right. And a question that came in from Samir is around how soon can we see KARNO set up in BEV charging? So our deployment plans are the second half of next year is when we're actually going to start some of these customer deployments. Great news is we have actually numerous parties on the BEV charging side of things that are intrigued and want to deploy the KARNO in their applications. And maybe just to talk about that. So what they're facing is they're trying to go out and deploy 50 EV charging pedestals, and they're going to their utility provider, and their utility is telling them, hey, come back in 3 years and maybe we can then give you a grid interconnect. Or we even heard out in California, one was quoted even closer to 10 years, or there was another instance where the utility just flat out said, until we start building more power plants, we are not going to have the capability of putting an EV charging site at your location. So these are some of the pain points that EV charging sites are facing. So as they look at the KARNO, they're looking at it as a way that not only can they deploy the EV charging setup faster, right? Because once we're into production, then you're just bringing your own power plant and putting it on site. But now you're also offering the ability to be fuel flexible, as well as have a very high efficiency level and lower costs of electricity generation in most instances. So second half of next year is when we plan on the initial BEV charging setups to be put into place. All right, next question has come from Keith. So how does the KARNO compare to a diesel genset for fuel use or efficiency? And we've talked a little bit about the efficiency, but maybe fuel use and the difference there.
Yeah, fuel use generally is going to scale with efficiency. So if the KARNO system is running at, let's say, twice the efficiency of a comparable diesel genset, you're also going to get half of the fuel usage in that amount of time. Or maybe another way to look at it, if you have a fixed amount of fuel, like in a storage sort of setup, you could run twice as long in the same amount of time. So it scales 1-to-1 with efficiency. Fuel use does.
Yeah. All right. A question that's come in from Keith is, how does a hydrogen fueled KARNO compare to fuel cell in efficiency and fuel use?
Yeah, so compared to a fuel cell, I mean, there's lots of different flavors of fuel cell, but if we just kind of talk about it generically, generally the KARNO generators on a net basis is going to be very similar to that of a fuel cell. You're going to see very similar output, after all of the balance of plant and other items. So if you're just saying fuel in to electricity, usable electricity out, let's call them a wash for most purposes.
All right, so we're get a little technical here. So a question in from Samir is, does the DC output of the generator pose any concerns about harmonics in the electrical system? And are there any measures to place to address such potential harmonic issues?
Yeah, so I mean, every electrical installation is a little bit different, right? Yep. For example, when we do grid connected electrical systems, we often have an isolation element to it, right? To isolate your system to the grid. And so I would say that in general, it's not like a concern for every application, but in some it makes sense. On the demos we've done to like islanding or battery installations, we don't have any isolation required in those instances. So very much a case-by-case basis.
So also on the technical side is a question in from Keith, which is around the metals that we're actually using in the KARNO generator. And are those corrosive resistant from like salt air or water in the environment? So you want to touch on that a little?
Yeah, so the metals, we use a variety of metals, just like any application. Most of them are going to be your steels, your aluminums, your coppers, and then we use some cobalt-based alloys specifically for our hot side. And so for our hot side component that sees all of that hot gas and lives in that day in, day out, it is about a 50% cobalt alloy. And the beauty of that is that it's highly resistant to things like oxidation and corrosion that you would be concerned about for having, let's say, not so clean fuels. As an example, these inert elements are nearly impervious to those and gives us a huge advantage.
And a follow-up on that one was, will diesel fueled KARNOs meet the tier 4 requirements?
Absolutely, yes.
All right. A question that came in from Twitter. Apologies, I just lost the question. There it is. So from Ivan, which is, Also, getting a little deep on where we get the heat from here. So does the KARNO have additional applications, i.e. in nuclear or geothermal or hybrid solar, where you can actually use other sources of heat to actually produce electricity?
Yeah, this is a great question because we often talk a lot about fuel as a source of heat, and that's because, you know, in the infrastructure that we mostly have, that's the most practical. However, as we've, you know, hopefully said multiple times, the engine element of this generator itself only needs heat. Right. And so whether that heat comes from nuclear or geothermal or concentrated solar are absolutely valid ways to get that heat and then move it into the system. And for all intents and purposes, the system won't know the difference between heat entering that comes from nuclear versus heat entering that comes from fuel and a chemical release. It works exactly the same after that point. And so that is also what gives us a lot of excitement around the potential of just how, you know, future-proof a system like this is to those adapting sort of heat sources in the future.
Yeah. And, you know, one thing that we've even discussed is as you think about that linear generator setup, you have the three outer parts and then the linear motor in the middle. If you change what type of heat source you're using, it's really only the end part, the reactor, that actually needs to change, right? The heater, the chiller, the actual genset, that can all stay the same, because that sealed you know, middle section there, all it needs is heat coming in, and that's what's going to make the electricity. So it's a fascinating concept. We've obviously had a lot of discussions with like customers around this, and it's very common that you get into the call and people think it's a linear internal combustion engine, right? We've heard it time and time again, and then it takes a little while to like, wait a second, this thing actually makes electricity off of heat and gas is expanding. Like you need to change the way you think about it, but it's almost like the difference between a internal combustion engine and a fuel cell, right? We're we're a different way of producing electricity.
We're really heat in fuel, or heat in electricity out, as opposed to fuel in electricity out. Yeah,
it's a good way of thinking it. All right. So a question that came in from John is, if natural gas was available, how would you determine the economics of using the KARNO as a prime power source? So it's a good question. I mean, the best way to think about it is if you have natural gas, you're going to know what your cost of natural gas is, and then you're going to have about a 50% efficiency of converting the BTUs of natural gas into kilowatt hours of electricity. And so, that's the very simplest way. That's how we usually calculate it for customers. It's just a 50% efficiency. Now, there is another element that we get into when we're talking with people about prime power applications or industrial applications, which is there a way to use the wasted heat, right? So there's combined heat and power cycles, which allows you to not only have our 50% efficiency of taking the fuel and making electricity, but now there's also that other 50%, or not exactly, because there's some losses due to blowers and things like that, but maybe another 40-ish% of power that is heat, right? And or energy that is heat. And so if you have a facility actually like our one up in Ohio, where there's a thermal loop already in the building, we can just pump that heat into that and use that to heat the building.
Absolutely. Yeah. Combined heat and power, you can achieve total efficiencies in excess of 95%, which just, again, lowers that operating cost significantly and almost makes the application a no-brainer.
One question that's come in from Dave is, has the KARNO engine to date already received any emission certifications, or maybe talk about the path to get there?
Yeah, so no certifications like officially yet, but we all of our testing, we test to the same standards and using the same process that will be used to achieve those certifications here in 2024. And so we have high confidence that we will comply to all those, but no certifications yet officially.
Another question in from Donovan from Northland Capital is, I have a question about the use of untreated natural gas in the Permian. Since this untreated gas would presumably have some impurities, where do those impurities go if they don't turn into emissions or pollution of some kind?
Yeah, so the way to think about the system is we take all the hydrogen bonds that are in the system, or as many as we can, we break those apart, right? So whether those are a hydrocarbon or just hydrogen, we pull the heat out of those, the energy. But anything that it does not participate in that reaction, like sulfur as an example, is going to just find its way out the same way basically that it came in. And so we do need to make sure, we work with customers very closely on making sure that they comply with all the emissions requirements for that. But from the perspective of the KARNO generator, it doesn't really see those or have any influence on those whatsoever, kind of in and out the other side.
Another question from Samir is, what is the minimum and maximum load in comparison of a 30 to 80% for conventional generators? So this is a great question. If you think about like the normal efficiency of an internal combustion engine, there's kind of a sweet spot that you would want to operate it in where you're going to get most efficient use of the fuel. If you're below that sweet spot, then you're going to have a less efficiency, or similarly, if you're well above that sweet spot at like 100% power, your efficiency goes down, even though your power level is going up. With the KARNO, what's really unique is it's got a very flat, in comparison, efficiency curve, right? And so I think is around, we're saying like 40 to 100%. Is that, or
yeah,
what,
kind of the sweet spot?
Yeah,
kind of that 40 to 100
would be where you're getting a pretty flat efficiency band within the KARNO. And this is great for applications where you might have oscillating power levels. Now you're not giving up really, you're not giving up a lot of efficiency if you need to change how much power you need. The other big advantage we see in that regard over fuel cells is, for anyone who's really familiar with fuel cells, they can have a very high peak efficiency, very comparable to our peak efficiency. But then as you get into high power levels, it falls off a cliff, right? The efficiency becomes very bad if you're up at about 100% power output. So now what fuel cell providers are doing is they're saying, hey, you're going to really want to operate this maybe around like 60% power or somewhere along those lines. So size the amount of fuel cells you need so that you're only running them at 60% power. Well, the problem with that is that becomes very costly, versus we're quoting a 200 kilowatt generator, and we're telling customers, no, you can really run this thing at 200 kilowatts.
Yeah, when we quote this rated power, which is 200 kilowatts, the intention is you will run at 200 kilowatts and it will sit there potentially its entire life, and that's how it's been designed.
Yeah. Another question in from Keith, which is, how do you switch between fuels, and can it be done on the fly?
Absolutely can be done on the fly. That's a great question. So the beauty of, again, this continuous reaction process is that as the fuel content changes, or as the energy content changes in that fuel, the system can automatically sense those changes based on how the temperatures are trending, as an example, and will adjust to compensate those. And the easiest adjustment and most practical is simply flow rate of that fuel. You need a certain grams per second for one energy content, you need a different one for another. And so that can happen seamlessly, and at any moment, without alerting the system that it's happening, it will self-detect that and adjust for that.
Question in here around regulatory hurdles as well. And do we see any regulatory hurdles that could impede the adoption of the KARNO generator? And this question is coming from David on Twitter.
Yeah, so from a regulatory standpoint, I mean, we're working to meet and exceed all of the known and foreseeable regulation. And so we do not see today any showstoppers relative to that. And we're going to continue to try to exceed all of those with margin.
So a question coming in from Hatem, which is, what is the manufacturing period for KARNO generators in the bigger scale size? So 1,000 to 1,200 kilowatts. So maybe just first thinking about like, how do we get to 1,000 or 1,200 kilowatts? So our plan is actually that those shafts that we showed you, which in production will be about 50 kilowatts power output, we're just going to kind of duplicate those in order to produce higher power levels. So if you needed 500 kilowatts of power output, that's roughly 10 shafts that you would need in order to produce that level of power. So as we think about 1,000 kilowatts, that would be you would get 5 of these 200 kilowatt 4 shaft systems in order to meet that power. So this is very different than a maybe internal combustion engine, where you hear those companies talk about they have a 12 liter, a 15 liter, a 70 liter, a 90 liter engine, right? Where they actually design entirely different generators based on the power levels. The KARNO is very different, where now we just stack these shafts together in order to meet the desired power output. So our plan in terms of bringing this into production is our first units are going to be 200 kilowatt hour box or 200 kilowatt boxes. And then you could stack those together. And then we also see on our roadmap doing a 2+ megawatt container, which would be about the size of a 20-foot shipping container, where you would have a bunch of those shafts on the inside, and then you would combine together the radiator fan cooling loop system, versus in those 200 kilowatt boxes, you're actually going to have independent cooling loops per each 4-shaft setup. So in terms of getting to those higher power levels, we can do it with those 200 kilowatt boxes because you just stack them together. Or our plan is also to introduce a 2+ megawatt container size unit as well. All right, the question in here from Gordon is, will the KARNO be used for freight rail applications to possibly replace or assist existing diesel electric powered engines? So this is an area that we are exploring. It's probably not going to be the first use case for it, but one that we do see as a great application of using KARNO in the rail sector, which, as you mentioned, a lot of locomotives today are using diesel and diesel gensets that actually already convert it into electricity. Yeah, and then it's an actual electric drive locomotive. A lot of those players have also started experimenting with hydrogen and fuel cells. So we see the KARNO as a way where you could actually kind of make a fuel agnostic locomotive, and then you could power that off hydrogen, natural gas, diesel, or whatever fuel is available in that area. So once again, it's probably a great use case. Not the first thing we're going after, but it is something we are exploring. Question in here from Magni, which is, can you tell me more about the adoption in the oil and gas industry and how to evolve out, and how it will evolve out to customers? So we mentioned this morning that we tested the initial gas coming out of the Permian Basin. That actually came from a customer, someone that we're working closely with, and that was the initial showcase of, hey, the KARNO can actually run on this fuel. We're now in discussions with that customer around getting them into the early adoption program here for the KARNO generators, and so more to come on that in the not too distant future. But the way we're thinking about 2024 adoption here is we're going to be limited, or at least how we're looking at it now, we're going to be limited by the number of units we have versus the demand that we're seeing from individuals. So what our plan is we're going to space those units out into a couple of different industries. So oil and gas, we're thinking, is one of them. EV charging is one. Prime power is one. And then what we'll do is build the backlog of customers in those different sectors and showcase to them those initial deployments, and then kind of use one customer in a specific use case to kind of prove that use case, and then use that to springboard into other potential customers in that space as well. So we're being really specific on who are going to be those initial adopters, what industries are they in, and trying to make sure that we cover a few of those different use cases, as opposed to putting all these just into oil, gas, or putting all of them into EV charging. A question here from Yaron is, current size is 50 kilowatt per shaft. What do you think the max size of future units will be?
Yeah, I mean, from a thermodynamics perspective, there's not a maximum that says this, thou shalt not exceed. Well, really, the reason we settled on this 50 kilowatt size was to kind of find that right balance between power, the applications that it would go into. So, not having too many for large applications, too few, but still meeting the needs for the smaller applications. But then in addition, our manufacturing process today does have some limitations around the size that we are. And so we've sized it to kind of optimize all those parameters. And I think that size is probably the right size for the near future. But we certainly, as opportunities arise or as use cases arise, will explore other sizes also. I would say it's probably more likely for us to even go smaller before we go bigger in shaft size, just given that 200 kilowatt minimum limit is still maybe above some of the use cases we could go and provide a solution for.
And in our investor day, which is back in June, we even showcased that on our roadmap. Not only do we see scaling up to that 2+ megawatt container size, which still the shafts stay the same size, you just put more shafts together, we do see an opportunity of moving to like a 10 to 25 kilowatt, more of like a household generator
Right.
size unit. Actually, it's pretty funny when we're having these customer discussions. All the customers, they're looking at this from like they're adopting it commercially at large buildings. They then say, well, when can I get a household unit one, right? Can you put me first on the list for one of those? Just because I think people really like the idea of, don't buy a generator for out back your house that only gets used a couple hours a year. Buy a generator that becomes prime power, and now the grid is your backup. So we'll take just a couple more questions here, but one in from David on Twitter is, how often does a KARNO generator require maintenance, and what is involved in the cost and downtime associated with that maintenance?
Yeah. So the maintenance there are no regular, I'll say, maintenance items. It's not like, there's no oil that you have to change. There's not elements that need regularly serviced, right? The system will watch its own health and obviously alert you if an anomaly arises. But the first planned maintenance activity is going to be around that 20,000 hour mark on average. During that maintenance, we would anticipate there would be a single piece part replacement. So the component that has reached end of life, you'll replace that. In our lab, we could do that entire thing in a day, 2 days. I think from a probably good opportunity to do a layout and inspection of everything, I would anticipate sort of a week timing for that.
Question in from Hafiz is, what is the maximum duty cycle of the genset, and are there considerations for continuous operation in these specific applications? So maybe to touch on the continuous operation, that is one of the big unlocks of the KARNO is we want this thing to be running 24/7. We want it to run continuously because it's designed in such a way where it's just inherently have such low maintenance, right? There's no oils, there's no lubricants, there's only one moving part. And even that part, it actually rides on what are called air bearings. So best way to think about it, it's like a air hockey table, right? When you're playing someone, that puck is just kind of floating along the top of the table. Well, that's almost what's happening with that shaft, even to a greater extent. And so it's designed for inherently low maintenance. And so from that standpoint, if you have one, you want to run it. And last question we'll take here is from Donovan, which is, would the commercialization of the KARNO generator for the use in oil and gas markets, once again, mean developing a trailer-mounted version, or is this something that can be made small enough to fit in the bed of a pickup truck? So to give you kind of rough dimensions of this 200 kilowatt box, and this includes not only the 4-shaft system, but then also your DC to AC converters, as well as your fans radiator setup, we're looking at about a 2-foot wide box, but then is about 8 feet by 6 feet. So from a dimension standpoint, our intent is that, these will get brought out to sites on a trailer, and then they could be deployed and be stacked next to each other to be very energy dense from a space standpoint. That's actually something we've seen compared to some of the other clean tech solutions out there. Our footprint is in the order of magnitude of like 1/10 compared to some of these other ones. Not all of them, but some of them. So we actually see that this has a really strong energy density, and will allow for people to deploy or take a pretty small amount of land and actually deploy a pretty good amount of power output. So with that, maybe just in conclusion here. So we threw a lot of information at you. Appreciate all the great questions. We went pretty deep on the technical side in some areas. We like to joke. Josh can go basically as deep as anyone wants to go on the technical side. So appreciate some of those great questions. But hopefully this gave people a snapshot of where we are at today with the development of this KARNO generator, some of the opportunities, the unlocks that this produces compared to other generator solutions or power solutions. But want to be clear that we are still in the development of this solution, right? We are running it at our facility. Next year, as we've mentioned, is when we actually move that to deploying it with customers. So today hopefully gave you a good snapshot of where we are today. And this will continue to evolve. So some of the things that we mentioned, like power outputs of shafts, we'll continue to tweak those, what fuels it could be run on, right? We obviously just announced this morning that successful testing with gas from the Permian Basin. So we still have a lot of exciting things ahead of us here. The technology development is going very well. There's an amazing team behind this, working on this every single day to bring this into commercialization. And we continue to thank all of you for logging in, joining these discussions today, so you you can be a part of this journey with us as we bring this solution forward, and hopefully bring a solution that truly can really change the way we think about distributed power generation and where you can actually source your electricity from. So thank you for joining us, and we hope to chat again soon.